we are going to be solving the question above. It says a water main of 500 mm internal diameter and 20 mm thick is running full. So it means that the water main is nothing but a what? A hollow pipe. You understand? So you can see the diagram. You can see this from this point to this point is 20 mm, and from this point to this point is 20 mm. So the total diameter is is going to be 540, because from here to here is 20. This place too is going to be 20, and this place is going to be 500. So from this point to this point is going to be what? 540. All right. So, and they said the water main is of cast iron and is supported at 2 points 10 meter apart. So here is the cast iron, and it is 10 meter supported at 10 meter apart. So you are going to note that the load on this cast iron is nothing but a UDL. All right. So they said we should find the maximum stress in the metal, then the cast iron and the water weight 72,000 Newton per meter cube and 10,000 Newton per meter cube respectively. So here is our given data. The internal diameter is 500 mm, so which you convert to meter, divide by 1000, and the thickness is 20 mm. All right. So here we have our outer diameter. You know, the formula for outer diameter is equals to the internal diameter plus 2 multiplied by thickness. So you substitute, you are going to have 540 mm, convert it to meter. All right. So the weight density of the cast iron, we are given the weight density to be 72,000, and the weight density of water is also what? 10,000 Newton Newton per meter cube. All right. So the first thing we are going to be doing here is to calculate the internal area of the pipe. The internal area of pipe. So we are going to denote that with A subscript I. All right. The formula for that is pi. Then since we are dealing with internal, the diameter too is going to be what? Internal. This square divided by 4. So this is what we are going to have. All right. So if we substitute now, we are going to have pi multiplied by the internal diameter is going to be 0.5 squared divided by 4. So if you do your math correctly, you are going to have this to be equals to 0.1960 meter squared. That is, it is area. So area is squared. All right. So, and you are going to take note carefully that this internal area that we just calculate of the pipe is also equals to the area of the water section in the pipe. The area of the water section. Let's write it. Is equals to the area of water section. So everything will be equals to 0.1960 meter square. All right. So now the next thing we are going to calculate here is nothing but what? It's nothing but the outer area of pipe. Outer area of pipe. So outer, that is A subscript. That is outer area of pipe. So it's going to be pi d naught squared divided by 4. This will be equals to, so this will be equals to pi, then multiply by d naught. What is d naught? So d naught is 0.54 divided by 4. This one is squared. So let's just leave this to be in this form. That is meter. The unit is going to be meter squared. All right. So that is what we are going to have. Now, the next thing we are going to do is to calculate the area of the pipe section itself. The area of the pipe section. You know, the pipe is a cast iron that is nothing but a what? Hollow. So the area of the pipe section itself. Area of pipe pipe section will be equals to, now since it is hollow, we are going to be taking this to be pi all over 4 into what? Into d naught squared minus di squared. That is outer diameter square minus what? Internal diameter square. So if we substitute, we are going to have this to be equals to, I don't know if I can shorten this because I want to maintain space. All right, so area of the pipe, so pipe section. So let's represent it to be what? AP, so that everything will just be on a single line. But please, you can just write it in full, please. All right, area of the pipe section, so A subscript P will be equals to, so this will be equals to pi all over 4 into d naught squared minus di squared. All right, so this will be equals to pi all over 4 into, so our outer diameter, that is 0.54 squared minus what? Minus the 0.5 squared. All right, so if you press this in your calculator, you multiply by pi and you divide by 4, you are going to have nothing but what? 0.0357, 0.02, sorry, 0.0327 meter squared. So this is what we are going to have. All right, and so we are done with the area of the internal diameter, then which is also known as the area of the water section, and the area of the outer section, and here is the area of the pipe section. All right, so now since we are done with this, now the next thing we are going to do is to calculate the moment of inertia of the pipe section about the neutral axis. The moment of inertia of the pipe section above the what? Neutral axis. So here, you know, moment of inertia is denoted with what? I. So this is pi all over what? All over 64 into what? Into d naught to the power 4 minus d subscript I to the power 4. So if you substitute here, you are going to have nothing but what? So this is going to be pi over 64 into, so d naught is 0.54 to the power 4 minus 0.5 to the power of 4. All right, so this will be equals to, so this will be equals to 1.105 multiplied by what? Multiplied by 10 to the power of 9 mm to the power 4. So this is what we are going to have. All right, so this is the moment of inertia about the pipe about the what? Neutral axis. All right, so now we are going to find the weight of the pipe section and the weight of the water for 1 unit length. We are going to find the weight of the pipe section and the weight of water for 1 unit length. All right, so let's go for the weight of the pipe section. So let's denote this with W subscript P, weight of the pipe section. Please, you can write it in full, please. Weight of the pipe section for 1 unit length. That is, we are going to take our length here to be equals to what? 1. So the weight of the pipe section here is going to be equals to what? Weight density of cast iron. Weight density, let me write this in full. Weight density Okay, I have written it here. Weight density of cast iron, good. So which is denoted by P subscript C. Multiply by what? Multiply by the volume of pipe. Multiply by the volume of pipe. All right. So this is weight density of cast iron multiplied by the volume of pipe. So we want to find the weight of the pipe section. All right. So now, and we know that this our volume is nothing but what? Area times what? Times length. So here is going to be the what? It's going to be the area of the pipe section. The area of the pipe section, and which we have calculated here. So here we are going to have this to be equals to, this will be equals to, that is weight density multiplied by area of the pipe section multiplied by what? Length, right? So if we substitute, we are going to have this to be what? This is going to be 72,000 multiplied by the area of the pipe section. So the area of the pipe section is nothing but what? Is 0.027. Then multiply by our length. We said for what? 1 unit, for a unit length meter. So it's going to be 1. All right. So if you multiply all of this stuff together, you are going to have this answer to be what? 2354. 2354 Newton. All right. So now the next thing is we are going to find the weight of what? The weight of water. The weight of water. So let's just take this as water. We can put H2O here, weight of water. All right, something like that. All right, so just in a similar way, so this is going to be weight density of water, weight density of water times the volume of water. All right, times volume of water. And our volume of water here is going to be what? It's going to be the area of the water section times what? Times length. And don't forget, I have already told us that our internal area here is equals to the what? The area of the water section. So here the formula can be written as PW multiplied by what? Multiplied by A I naught multiplied by L. So this will be equals to 10,000 multiplied by 0.1960 multiplied by 1. So if you multiply all of this together, you are going to have 1,960 Newton. All right. So the next thing we are going to do is to find the total weight of the pipe for 1 meter. For 1 meter, the total weight of the pipe, the total weight of pipe. So let's put that to be what? W subscript T. The total weight of pipe for 1 meter. So it means it's going to be equals to the weight of the pipe, plus the weight of water, plus the weight of water. So if you substitute now, this is going to be 2,354 plus what? Plus 1,960. So this in total is going to give us what? It's going to give us 4,304. 4,314 Newton. And 5 plus this, yes, yeah, that's correct. So 4,314 Newton. All right. So this weight that we calculate here is the weight that is due to what? UDL. That is uniformly distributed load. All right. Which is also W. Is that clear? So we are going to be using W, which is going to be equals to the total weight. So everything will be equals to 4,314 Newton. All right. So we have already said that this total weight, it is due to what? Uniformly distributed load. So we are going to consider the maximum bending moment for a simple supported beam that carries a uniformly distributed load. And of course, if you have been following this course from the beginning, we have already discussed all of that in our lecture on the application of Fleischer equation. So you can watch that. All right, so the maximum bending moment due to UDL is equals to what? It's nothing but what? WL square over what? Over 8. Over 8. So if you substitute now, the WL, which is the load, that is the total load or the total weight, anyhow you want to call that, is going to be 4,314 multiplied by the length. The length is what? Is 10, right? So we are going to be using 10 square here, then divided by what? Divided by 8. So it means that the maximum bending moment will be equals to, if you press this, you are going to have nothing but 53,925. 53,925 so it's going to be Newton meter. All right, so now if we want to take it to Newton millimeter, we are going to multiply by 1,000. So we can write this as 53925 times 10 to the power of 3. Then it's going to be Newton mm. So this is going to be the what? This is going to be the maximum bending moment. All right, so the next thing is to calculate the stress, the maximum stress which we are asked to calculate. So let's clean this part. So if today is your first time of coming across our content, please kindly click on the like button, click on the subscription button, and turn on your notification in order to receive our video anytime we post. And please don't forget to also share this content with your friends who might be in need of it. All right, so let's continue. Now we are going to be applying the Fleischer equation. Of course, we have discussed the Fleischer equation. We have proved the Fleischer equation. So which is M is the maximum bending moment over I, which is equals to what? Which is equals to the maximum stress over Y. So if we make the maximum stress the subject, so this will be equals to M over I multiplied by Y. This Y2 is going to be, this one is maximum. This one too is Y max. All right. So we already know our maximum bending moment. We know our moment of inertia, our Y max. Our Y max for a hollow circular section is d divided by 2, that is the outer diameter. So which is 540. So it's going to be 540 divided by 2, and 540 divided by 2 is 270 mm. So this is going to be 270 mm. All right. So now let's calculate our maximum stress now. So which is maximum bending moment, which is 53925 times 10 to the power of 3 divided by I, that is the moment of inertia, which is 1.105 times 10 to the power of 9, then times our Y max. Our Y max is 270. All right. So if we do this, we are going to have the maximum stress, which we are asked to calculate here. So if you press this correctly, you are going to have your answer to be nothing but what? 13.18. So Newton per what? Per mm square. So this will be the answer for the maximum stress. So this is how to go about this question. I believe we understand this. Stay tuned for more and more questions. Thanks.